So in our last lecture, we began to think about fluid flow, and we began to think about hydraulic head and the fact that hydraulic head is the sum of our elevational head and our pressure head. So if it's the sum of our elevational and our pressure heads, how did we kind of come to get this equation, generally speaking? So we actually can think back to some of our early maybe physics classes that we've taken. And we can think about the fluid flow equations that we've seen. And our graph, that total head calculation, right, actually can come from thinking about Bernoulli's equation. So we can kind of, let's go back and think a little bit more about how that came to be. So let's first start out with this idea of head in a little bit more detail. So King Hubbard in 1940 said, "A potential is a physical quantity capable of measurement at every point in the flow system, whose properties are such that flow always occurs from higher values to lower values." So remember, in our last lecture, we talked about this idea that water flows from high head to low head. And so here we're again talking about the same idea. So we can think of other systems where we have this transport. And so heat or temperature is one of these good examples where heat is going to conduct from high temperatures to low temperatures. And voltage is the same way. Electricity is going to go from a high voltage to a low voltage. So we often just call this this difference voltage as we're taking a look at it. So what we're trying to think about today is how we came up with and the factors that are influencing fluid flow in groundwater. So remember from back in physics, a potential is the work per unit mass, right? So this is our potential here. This is our potential. This is our work. This is per unit mass. And you're going to see a couple of equations as we're moving through here. So feel free first just to maybe listen and then to write them down later. And not to get too nervous about what these equations look like, because really they're just trying to talk us through what are some of the details that we've already just said. So when we think about fluid potential, this work per unit mass, we need to start with a physics definition of work, right? Which is the energy required to move a fluid from this point, Z at 0, our datum, right, to some point here above it, right? That's all we're really thinking about. So we have to ask the question, what is the work that is actually done? So the work that is done is we have the work to lift the mass. We have the work to accelerate the mass. And we have the work to change the fluid pressure. So these are the three types of work we are going to have to sum up, right? All three of these have to be considered when we're thinking about the work that's being done to move water in the ground. So let's start with the very first one. So our first work that we're going to think about here is the work to lift the mass, right? So it's just going to be mass times gravity times that distance it was lifted. The work to accelerate the mass, right, from a 0 to the velocity that it's moving at is the mass times the velocity squared divided by 2. And then finally, the work to change the fluid pressure is the change in pressure between your starting point and this new elevation that you may be at Z. So we can think about what this looks like, and don't be too nervous about these integrals that are down here. What I'd really like you to focus on is just the end point of this integral here. And just thinking about the idea that it's the mass times the integral of 1 over the density times the change in pressure, right? So really, we're just talking about a function that's influencing the change in pressure and the density of the fluid itself. So here are our 3 work components. So now what we're going to have to do in terms of thinking about this, right, is we're going to have to begin to sum them up. Now, it is important that when we put in these terms down here, just to get an understanding of how we transitioned from this integral over here, which was volume, to what we have over here, is that our density is just a volume per mass. And so we're just kind of substituting one thing out for the other. So again, a potential is work done per unit mass. A fluid potential is just the sum of the 3 different types of work being done per unit mass. And so the only thing that's dropped out of here is that each of these terms before had a mass term to it. But if we have all of those mass terms, we can actually begin to remove them, right? So inevitably, what we end up with here is Bernoulli's equation, which is a fundamental equation of movement. So flow in pipes or channels, etc. So that's really what we're taking into consideration. So we have our work per unit mass, right? Our work to accelerate and our work to change the pressure that we have here. Now, one of the nice things is we can actually, to get to the groundwater kind of equation that we saw before, to get to that total head equation we were looking at, we can actually simplify the Bernoulli's equation for groundwater. And the reason we can simplify it is that velocity is very, very small, almost negligible in groundwater systems. So that's the first one. So why can we be able to simplify this equation? First is that the velocity is very small in the groundwater systems and therefore can be considered negligible. The second one is that water is quite incompressible. So density changes with pressure are really small. So because of that, we can therefore approximate the integral as just the change in pressure from our datum to our point of interest divided by the density. Again, so we have small velocities that allow us to reduce the equation. And because water is incompressible, we also get to reduce the equation. So therefore, what we're left with is fluid potential, right, which we've been talking about today, total head, is equal to gravity times some elevation, right, times the difference, or plus the difference in our pressure divided by our density. So then what we can do, right, that's not exactly the equation we saw earlier today. So we can actually rewrite this equation to look a little bit different and look a little bit more like the equation you saw earlier. So we can write this to create something slightly more simple. And what we can do is we can talk about what our pressure actually is. So this value, when we think about the pressure that's here, another way of writing that same pressure that we're taking a look at here is the initial pressure that we had in the system, and that pressure that's sitting just at this water level times density times gravity. So we can say our pressure is proportional to the amount of the overlying water. That's another way of saying it. So the amount of water overlying this point here, right, is proportional to the pressure. And that's all we're saying. So if this is true, we can go ahead and plug this value in for our P here, for our pressure. And then we can go ahead and we can rearrange the equation so that we get that our fluid potential is equal to gravity times Z, or our elevation, times gravity times our pressure head that's here. So that's another way of us thinking about it. And then we could simplify this even more, removing gravity from the situation, and then we end up with the calculation that we had. So here's us removing gravity times the head. And so when we divide, I guess we'll go back 1 second. When we divide or multiply our head by gravity, we end up with our fluid potential. And so when we think about our head in general, we can think about head as just being the sum of our elevation head here plus our pressure head, or the fact that we can take that pressure head, which might be in a depth unit, right? So centimeters, meters, and we can put it back into a pressure unit here, right? So we have our pressure divided by our density times our gravity. So head is called the hydraulic head, or the total head, or just head. So yes, you'll hear these different kinds of terms that are used. So put them all on your equation sheet to be able to identify what H is. G is always approximately the same everywhere. So H is proportional to the fluid flow, or to the fluid potential. This means what this means to us is that groundwater flows because of changes in head. So this is very important because what we're doing is we're thinking about the water level in a well, right? And we're comparing it to the water level in another well. And this is allowing for us to understand the direction at which water will flow as a result of this change in head.